change my format to the official one. Okay, so hi everybody. I'm a theoretical physicist here, and one of the things I work on is antimatter, and in particular, I work on trying to explain why we see more matter than antimatter today. So, okay, first point, we exist for now. So here's a very nice picture from the Hubble Space Telescope looking at other galaxies. And these other galaxies, we think they have planets. We don't know if they have people on them or anything else like that, but at least there are other galaxies. And our universe is full of stuff. So we're here, other stuff is here, we exist. So one implication of this, the fact that we exist, is that matter, and by matter, I'm going to use a slightly different meaning than Martello, matter, stuff with mass. Matter is stable. Regular matter is stable. And I'm going to flash, this is my only equation, and I think everybody's familiar with it, E equals mc squared. And what this equation says is that the mass that you associate with matter, this is the m here, is in fact a form of energy. So I carry a lot of energy just because I have mass. And the relationship between my mass and the amount of energy involves a factor of the speed of light squared. So this is the famous Einstein equation. Now, if you look at this and you start to think, so if matter's a kind of energy, what's stopping regular matter from just going poof and turning into pure energy? And that obviously doesn't happen. It's good it doesn't happen, because if we just went poof, we wouldn't be here. So we exist. It doesn't happen. But the question is, why doesn't it happen? So it seems to be perfectly consistent with E equals mc squared. And our explanation for why it doesn't happen involves something called charge, and the idea that charge is conserved. And what I mean by conserved here is that if you start with a certain amount of charge, you're going to end up with the same amount of charge at the end of the day. So the amount of charge, the total amount of charge never changes. So if we think about our matter, along with this idea is the extension that matter carries charge, but what I call pure energy doesn't carry any charge. So we take this and we think about E equals mc squared versus, can I convert matter and energy just for free? The answer is no, because of charge conservation. So if I count the energy, matter has some amount of energy, mc squared, corresponding to its mass. And in principle, the amount of energy I would get from converting the matter into energy would just be mc squared. So the amount of energy would be conserved. The amount of initial energy would be the same as the amount of final energy. But I can't do the same for charge. So if I say that matter carries a charge, let's say the charge is +1, the number doesn't really matter, just as long as it's not 0. If matter carries some charge, energy doesn't carry any charge, and charge conservation says this can't happen, because I need to keep the same amount of charge at the start as at the beginning. So this idea of charge conservation is hugely important because we're here. If we didn't have charge conservation, in principle we just go poof, we wouldn't be here, and it wouldn't be a very exciting sound. Okay, so we've also heard from these various talks that antimatter also exists. And again, I can go back to my E equals mc squared equation. And now I can wonder, suppose I could take matter and smush it together with antimatter. Can I convert this into energy and vice versa? And the answer, it turns out, is yes. As Martello said, you can have annihilation, where if you take matter and antimatter, you smush them together, this turns into energy. That goes in this direction, but I can also go in this direction. If I take enough energy and I cram it together, in principle I can make a combination of matter plus antimatter. So this happens, and this tells us something about charge. And before I do that, here is a nice experimental results showing the creation of antimatter. This thing going out here is matter, this thing going out here is antimatter, and the same here and here. And what's happening is that I have a lot of energy coming in. So in this experimental apparatus, you don't see the energy coming in. So there's energy coming in, it's a lot of energy, you can't see the experimental apparatus. But what you can see is the matter that's produced. So what happens is I have a lot of matter coming in, and I create a matter-antimatter pair here, and I make a matter and antimatter pair here. This thing, just maybe close your eyes, don't worry about that. This just turns out to be a little bit of debris that is itself. So maybe focus on this one. So here I'm turning a large amount of energy at the start into a matter and antimatter combination. Okay, so for this all to work, antimatter has to essentially be identical to matter, except that it has the opposite charge. So if you want to maintain this charge conservation idea, an energy conservation idea, and the fact that I see experimentally that matter and antimatter can convert back and forth to energy, I can look at the amount of energy of matter, the amount of energy of antimatter. So here, the matter has mc squared. The antimatter has exactly the same mass, so it also has the same sort of mass energy, mc squared. And together, they give you 2 mc squared of energy. But now if I look at charge, the charge of matter would be +1. The charge of antimatter has to be opposite to it, so -1. So that means the total amount of charge I start with adds up to 1 minus 1, which is just 0. And this is exactly the same as the amount of charge I have at the end of the day. So charge conservation does allow matter and antimatter to convert back and forth with each other, provided antimatter is essentially identical to matter, except with a flipped charge. Okay. So from this point of view, antimatter, as Marcello said, it's actually not all that weird. Like it's unusual in that we don't see it around us every day. But compared to the stuff we know, it's basically the same thing, just with a flip charge. Okay, so this is nice. We see antimatter experimentally. We see the conversion of pure energy into matter and antimatter pairs. This turns out to raise another puzzle. And this other puzzle comes up if we look back in time. And by looking back in time, I mean look back as far in time as we can. And in particular, look at the early universe. So I'm just going to flash this. I'm not going to go through the whole idea, but our universe today has stars and galaxies and so on and so forth. But if we take our universe today, and we take what we see and extrapolate it backwards in time, using the laws of physics we know, what we deduce is that very, very early on in the age of the universe, when it was much less than a second old, the very early universe was very, very hot and very, very dense. And starting from this very early universe, the universe expanded and cooled off and eventually evolved to what we see today. So you can run the movie backwards, you can run the movie forwards, but it's a consistent story. So now, if I take this picture of a very hot early universe expanding and eventually evolving to our universe, there is an implication for antimatter. And that is, our early universe was really, really hot. It had lots and lots of energy. And in particular, if you look early enough in the universe, there's so much energy around, you can convert all that energy floating around into matter and antimatter pairs. You could create matter and antimatter. And the implication of this is that very, very early on in the history of the universe, there was lots of antimatter around. Just because there's so much energy around, you could create the antimatter by just smushing the other energy together. And this goes back and forth. Now, our universe today seems much different. We essentially see no antimatter. It's made of matter, not antimatter. And an obvious question is, why is this? So let me try a couple of things called thought experiments. So the idea is that we start with some assumption, and we think really hard and see where it takes us. So let's take as our first assumption that very early in the history of the universe, there were equal amounts of matter and antimatter. What would this imply? So if I start off very, very early in the history of the universe with equal amounts of matter and antimatter, and I let the universe evolve, that means the universe expands and it cools off. Eventually, as the universe cools off enough, there's no longer enough energy for energy to convert into matter and antimatter pairs. But on the flip side, if I have a lot of antimatter around, I can still take my matter and antimatter, push it together, and make pure energy. And if you take this picture and evolve forward, what it implies is essentially no matter is left at the end of the day. No matter, no antimatter, everything just annihilates away. So the result of our first experiment, thought experiment, is this: nothing. At least no regular matter. So this is obviously not the universe we know and love. So let's try another idea. And for our other idea, suppose the early universe had slightly more matter than antimatter. And let's go through the same process. And I think at this point I'm going to pause the talk, and we're going to do a little group activity. So we want to get some audience participation. So is this actually here?
Yeah.
Okay, so we're going to do a little activity involving cards and chatting with each other, and I'll actually.
Wow. So everyone sitting in the middle over here is going to have maybe these cards underneath your seat, if you look right underneath your seat. It's taped down. Everyone have a card?
You won't be annihilated in real life if you participate.
Yeah. Like, you're not actually antimatter and matter. So what happens is, in this game, if you have a green card, hands up, green cards. So you guys don't get to go to the US, at least not that type of green card. Instead, you want matter. So this is a matter card. And anyone who has the red one, hands up. So you guys are antimatter. And that means when you guys stand up, yeah, while you stand up, and I want you guys to mingle around a bit. So just mingle a bit, and you're just matter and antimatter just moving around. Yeah? Okay. Just let this go on for like, 15 seconds, 10, 15 seconds. Yeah. Right. Okay, now stop. Everyone stop. Go to the person right next to you, and let's see what happens. So, someone can Okay, everyone, stop. Okay, so now the person next to you, you know what color they have, right? So let's say the person next to you has green and you're green. You're matter and matter, right? That means you won't interact, you won't annihilate. So if that's the case, you repel against each other. Yeah, keep walking. So you just keep walking. Same for red and red. If you have red and red, avoid it. But if you have red and green, you annihilate. So you guys go back to your seats and you're Okay, so you guys pair up again. So you guys annihilated. Who else is left? Let's see. So what colors do you have left standing up right now? 2 reds. Okay, so what we made right now, we made our own universe, and we actually made an antimatter universe. So something different from what we had before. But in this case now, you don't have any more green cards, right? So they don't annihilate. And what does that lead to?
Yeah, so now we have an excess of, well, in this case, antimatter over matter. So we've just done a simulation, not quite a computer simulation, but a human simulation of what happens what seems to happen in the early universe, assuming that we started early on with more matter than antimatter. Okay, actually, we got the colors wrong. We had more matter than antimatter, but okay, you get the idea. So again, our thought experiment. So we actually did a real experiment here. So I'll just go through what the thought experiment would say. The universe would expand and cool. Eventually, the conversion of energy into matter plus antimatter would turn off, as you don't have enough energy anymore for that to happen. But you still have matter and antimatter annihilating into energy, because there's no barrier to this. And then, at the end of the day, all the antimatter will be annihilated away, and all that would be left would be the extra matter. So we just saw that explicitly. We just did our thought experiment. Well, we actually did the experiment. Science is an experimental activity. So the result is our universe. So the fact that we have more matter than antimatter is just a signal that even though very, very early on in the history of the universe, there's lots of matter and lots of antimatter, you still had to have just a little bit more matter than antimatter to get the nice galaxies and planets and us we see today. Okay, and we did this in a room with maybe, I don't know, 30 or so people. The actual numbers are much bigger. So it turns out that you would have roughly 10 billion plus 1 matter particles, and 10 billion antimatter particles, and you'd end up with 1 matter particle left over. So it would be like if we gave out cards to everybody on Earth, and everyone on Earth got together and did this, we'd be left with 1 person at the end of the day, still standing and not sitting. So these are large numbers. And this poses another puzzle, which is how do we get this extra matter over antimatter? I mean, we only need 1 part in 10 billion, but this is still something we want to explain. And one thing I work on is trying to explain this, and our theories of how we explain it go by the name of baryogenesis. So baryogenesis, baryo is Greek for heavy, massive. So the idea is we're making the extra mass, the extra matter. So there are a couple of challenges. We want to make more matter than antimatter, so we need to break this idea of charge conservation. And we need to make charge out of nothing. This is a bit puzzling because charge conservation is what's keeping us from going poof and turning into energy. The second thing we need is to distinguish matter from antimatter beyond just flipping the charge. Because we need to bias the processes that break the charge conservation to make more matter than antimatter. So let me give you one example. At this point I'm going to toss a lot at you, but I want to give you an idea of some of the things I work on. So one example of baryogenesis, one mechanism for baryogenesis is called electroweak baryogenesis. And here, very, very early on in the history of the universe, we have a phase transition. So the phase transition that we're probably all the most familiar with is if I put a kettle of water on my stove and turn it on, it boils. And that's a phase transition where I turn liquid water into steam. What's happening here in the early universe is I start with, if you like, the steam phase, and I cool it off, and eventually condenses into water, or at least an analogy of that. What's actually happening is I make bubbles that are a bit like water droplets condensing out of steam, but instead of being made of liquid water, these are made of, in a sense, Higgs. So these are Higgs boson bubbles. And once you create these bubbles, as things cool off further, these bubbles grow and expand and eventually coalesce, and everything is filled up with this Higgs phase instead of the initial steam phase. So I have this picture of bubbles expanding out in the very early universe in this phase transition. Now, let me say that we live inside one of these bubbles, or at least the remnant of one of these bubbles that's expanded and coalesced and turned into this one. So let's zoom in on one of the bubble walls. If we zoom in onto one of the bubble walls, what can happen is particles can scatter off the bubble wall, or particles could be transmitted through it. And because of something called CP violation, we'll hear about this a little bit more in the next few talks, you can actually distinguish matter from antimatter in a very delicate way. Next, to break charge, we have something called sphalerons. So sphalerons are kind of funny things that break this idea of charge conservation. And they have the effect of destroying antimatter instead of matter. So I take my sphalerons, I take my bubble walls, I put this all together. And one other thing is that the sphalerone process only happens outside of bubbles. It doesn't happen inside the bubble. We live inside a bubble, and that's good, because that means that the sphalerone process destroys charge in the early universe, but it doesn't destroy charge today, and we can still be here without going poof into energy. So the upshot of all this is a particular proposal for how we could have made more matter than antimatter. There are a lot of moving parts. It's very complicated. But various aspects of this proposal, this theory for how you got more matter than antimatter, can be tested experimentally. Some of the aspects of making the bubbles and so on can be tested at the Large Hadron Collider at CERN by testing the Higgs very carefully. The CP violation property is something we're searching for at the lab, and we'll hear a little bit more about this in the coming talks. Okay, so the lab itself touches on antimatter in a lot of other ways. We heard about alpha. We'll hear about UCN, I mentioned LHC, and there's also an idea that neutrinos may also connect to antimatter, and people will hear about neutrinos a little bit in a second. And let me just wrap up with a inspirational quote. So antimatter, in a sense, the reason that antimatter is so puzzling isn't that it's weird or mysterious or funny stuff. It's actually that it's not weird or mysterious enough. And the real puzzle, at least for me, is trying to explain why we have so much more matter than antimatter, given that antimatter is in some sense very much like matter.